Okay, Assalamu alaikum, everyone. Welcome to our today's lecture on selected topics, radiation physics series. Today is lecture 13. We're going to talk about dosimeters, properties, and examples of some dosimeters. Of course, this is not going to cover every dosimeter used, but what's really important is to focus on what properties we look for in a dosimeter. And then when a new dosimeter comes into the market, this is usually tested by researchers to see which of these properties, what advantages, for example, are for this dosimeter, what are things that one has to be careful of, and maybe we need a correction factors also. So what is a radiation dosimeter? A radiation dosimeter is basically, or the science of radiation dosimetry deals with measurement of the absorbed dose or dose rate resulting from interactions of ionizing radiation with matter. So this is what we mean by radiation dosimetry. More broadly, it refers to the determination. So we can do this by either measurements or by calculation of these quantities. We mean like the absorbed dose or the dose rate, as well as any other, quantity of interest relative to, radiation beams such as exposure, karma, fluence, dose equivalent, for example, energy imparted, and so on. Of course, in radiotherapy, we're more focused on getting the absorbed dose into different media for different radiation beams. So what we do, we often measure a quantity and try to derive from it through calculations based on some equations or relationships, another quantity. So for example, if we could measure the exposure, then we can take that quantity that we have measured and recalculate or calculate what would be, for example, the absorbed dose in air, or the air karma rate, for example, or even the dose in the medium, and so on. The past lectures, we have looked into such examples where using ionization chambers, we measure the dose in air or in the gas of the chamber, and then we start to use this appropriate cavity theory in order to convert the dose in the gas cavity to dose in medium, which is what we're interested on. So we derive these relationships, and then we convert whatever we measure to another quantity. The dosimeter is actually a device, and with it we can measure directly or indirectly one of these quantities. For example, an exposure, karma, absorbed dose, or energy or particle flux.
Sorry, Dr. Wamid, can't see your seats.
Sorry. I did not share that. Good you reminded me. Okay, so just to show you the slides. So basically, a dosimeter is, or radiation dosimetry is the science that deals with measurement of absorbed dose resulting from interaction of radiation with matter. Or we could actually broaden this definition to measure any quantity that is related to ionizing radiation, such as exposure, karma, fluence, and so on. Usually what we do is we measure one quantity of these, for example, exposure, and then we calculate from that exposure what would be the dose in air, what's the karma, what's the dose in medium, and so on. So the device used to measure these quantities. It's called the dosimeter. And usually a dosimeter will have some sort of a reader with it. And that the combination of the dosimeter and its reader is called a dosimetry system. For example, ionization chamber, we have the chamber and then we have the electrometer. So the chamber and electrometer, these are a dosimetry system. A TLD, for example, a TLD and the TLD reader, a device that reads the dose on a TLD, and that is actually a dosimetry system. So what is a dosimeter? A dosimeter can be defined generally as any device that is capable of providing a reading R that is a measure of the absorbed dose or exposure or any of these quantities deposit in a sensitive volume by ionizing radiation. So if the dosimeter, if that dosimeter does not respond to radiation, or if I bring something, for example, put it, let's say a sheet of paper, for example, and we put it, and I cannot claim it is put it in a radiation beam, I cannot claim that this sheet of paper is actually a dosimeter, because to us, nothing has changed before irradiation and after irradiation. But if we bring a film, for example, things are different. So film before radiation is exposed, it has a certain transmission, and then after radiation, then this transmission changes. So there has to be a quantity that changes, and then we read that quantity. So if we can read that quantity, then that's a dosimeter. These dosimeters usually they have a volume. So sometimes the dose inside that sensitive volume, their sensitive volume, is really not homogeneous. The dose might be in one location, might be a little bit different than those in another location in the dosimeter, or it's sensitive volume. But again, what we like to actually always attribute the signal or the quantity that we're measuring to a point, not to a volume. Let's say a point in media or a point in air. Okay. So if that happens, that the dose is not homogeneous throughout the sensitive volume, then the signal is somehow, it's a measure of an average of what's happening in the sensitive volume of this dosimeter. So the reading gives us an average dose actually in that dosimeter. So if you want the dosimeter really, want the dose to a point, we will try to find the dosimeter such that its volume is very, very small. The dimension of the volume is small. So at least it somehow ensures that the dose is not is homogeneous to some extent inside the dosimeter volume. We are not interested in measuring the dose inside the dosimeter or its sensitive volume. An example, we went through, for example, the ionization chamber, and we could measure a signal, and the signal could give us a dose in the air cavity of the chamber. But what we're interested on getting the dose in media when the chamber is not there. So there are we look at some examples, for example, the cavity theories, use of cavity theories, and so on, to relate the dose in the dosimeter volume to the dose in the medium of interest. Interpretation of a dosimeter reading in terms of the desired quantity is the central problem in dosimetry, usually exceeding the difficulty in actual measuring. So when we have a reading, we can measure, we can take the reading, but the difficulty is not really obtaining the reading. The difficulty is, again, converting that reading into the dosimetric quantity of interest. And as in chambers, we read a charge, but we're not interested in knowing the charge. We're interested in knowing the exposure, or we're interested in knowing the dose. So the conversion of that signal, the reading into the dosimetric quantity of interest, that is really could be challenging or could be difficult. So this is a schematic representation of a dosimeter. We have ionizing radiation. The ionizing radiation will produce some sort of a signal inside this dosimeter in this volume. And then we need to have an appropriate conversion factor, calibration factor, for example, to convert this measured signal into dose when we remove the dosimeter. Sometimes these calibration factors might not give us directly the dose in the medium, but rather they give us the dose in the dosimeter medium. And then again, we have to think of how we're going to convert the dose in the dosimeter medium to a dose into medium. An example would be, we have a ionization chambers, which has a dose, a calibration factor, N gas. So when we multiply the charge by the N gas of the dosimeter, it gives us the dose in the air cavity of the chamber. But we're not interested in that dose. We're interested in the dose when the chamber is removed in the medium. We're interested in the dose at that point. But we could have, for example, a chamber with an NDW calibration coefficient. So in that case, multiplying the charge by the NDW of the chamber immediately gives us the dose in the medium when the chamber is removed. Okay. So we looked at both of these examples. So this is the simplest formula for a dosimeter. So if you want the dose, we get a reading from the dosimeter, and then we multiply it by a conversion factor or a calibration factor. And basically, this factor converts this reading into a dose. A chamber would have its N gas, for example, or NDW. This calibration factor will have a units of grays per coulomb. That's a SI unit. Typically, it's usually centigrades per nanocoulomb and so on. But this is the simplest formula, formula for a dosimeter. But we know this is not true. In fact, a dosimeter, or this is the general formalism of a dosimeter. Yes, we have a signal, we have our conversion factor or calibration factor, but we have to take care of a lot of these, perturbations or corrections. We need to correct many things. So we need a multiple of correction factors in order to convert, our reading with the calibration factor into the dose. For N gas, for example, so we had the stopping power ratios, we have P replacement, P wall, P central electrode. Even for NDW, so we need a correction factor that was given by the KQ factor, especially, if you have an NDW for a specific energy, and then we want to get a correction, we're doing the measurements in a different energy, then we know that NDW is not valid, so we need to correct it. And that's why we need a KQ factor, which depends on the chamber model as well as on the beam quality. So sometimes these correction factors will be actually beam energy dependent, or will also be will depend on the dosimeter itself. So the desirable properties of the dosimeter. If we would like to have a dosimeter, probably we want this dosimeter to have high accuracy. And we'll define these terms. And we want this dosimeter to have a high precision. Another desirable property of the dosimeter would be, for example, we want it to be dose and dose rate independent. And gas, for example, is a dosimeter. If we're interested in dose to gas, actually that's the other one. That's the energy independent. So we want the dosimeter to be energy independent. Dose and dose rate independent. We want a dosimeter. It doesn't matter what's the dose rate. We still want the dosimeter to read the same signal. For example, if you imagine we have a chamber, and we're going to deliver to that chamber 100 centigrades of dose. but that dose will be delivered in 10 minutes, or it's going to be delivered in 10 seconds. So we have a difference in the dose rate, although the dose to the chamber is the same. So we would like that the chamber to give us the same signal, same reading, regardless of the dose rate or on the dose. Energy independent. Okay, that's for sure. We want it to be energy independent. Directional independence, that would be nice. It doesn't matter then, you know, the direction, the incident direction of the radiation towards the dosimeter. The signal will remain the same. High spatial resolution. We said the dosimeter, usually the reading is obtained from a certain volume. So if that volume is large, then okay, the dosimeter cannot resolve the dose, or it will have a lower spatial resolution. Sometimes this could be something we want, or sometimes no, we want a dosimeter with high spatial resolution to distinguish the dose, you know, to have a better resolution of the dose itself. Example would be measuring a profile of a beam, especially in the penumbra region. Penumbra region, if you have a large chamber, so you have a low spatial resolution, and then your profile might not be accurate because of what it's called the volume averaging effects and so on. We want the dosimeter not to be affected by the environment. So if I have a signal, or let's say the temperature change, or pressure change, or the whatever, we want the dosimeter response to be consistent. It is not affected by the environment conditions, only affected by the dose that was deposited in the dosimeter. And lastly, we want to have, you know, some convenience of use of this the dosimeter, and this will depend. Sometimes we want a dosimeter that immediately will give us the reading. Okay, or sometimes you want a dosimeter that can integrate the reading over a longer period. We might want a dosimeter that is reusable. We measure the dose and then we can use it again. Or sometimes we want a dosimeter that can only be used for one time, such that we have a record of the dose. So these are the properties of, or desirable properties of the dosimeter. So accuracy and precision. Accuracy and precision, these are these two measures actually the observational error. Accuracy refers to how close the measurement is to the true or accepted value. And the precision refers to how close the measurements or the readings are when we repeat the experiment several times. So precision is independent of accuracy. They're not the same. An example would be, imagine we have a dosimeter. The dosimeter, whenever it's exposed to the same dose, we're getting the same reading. That means this dosimeter is precise. But the dosimeter might not give us the correct dose, or it could be giving us something far from the true dose. This distance of how far is the measurement to the actual value, this is what we call the accuracy. So that's the difference between accuracy and precision. Results of measurements cannot be absolutely accurate, and the inaccuracy of a measurement result is characterized as an uncertainty. We want to measure a dose. Yes, we got the dose, but might not be true, the true value. We have some doubt on that measurement we obtain. So we attribute it, okay, an uncertainty or confidence level, how confident we are of what our measurement. So that's what we mean by uncertainty. So the uncertainty is a parameter that describes this dispersion of the measured values of a quantity. There are two types of uncertainties measurement: type A measurement and type B measurement. So type A is the best estimate of a quantity X. So type A, the best estimate of a quantity X is the arithmetic mean value of all measurements. Meaning, if we repeat the experiment again and again and again and again and again, and we're getting a dose multiple times, or even a reading multiple times, there might be actually differences in the readings every time we repeat the experiment. So we can estimate the error we can estimate the quantity, for example, what reading should we use to calculate our dose, and this would be the average of the readings that we obtain, and we can estimate actually what's the uncertainty in the dose for this type of type A error by taking the standard or taking the standard deviation. So for a type A uncertainty, and this is basically when you repeat the experiment, you get different values. So we can estimate what should be the value we use to calculate the dose, for example, or the quantity of interest by taking the arithmetic mean of the measurements. And the uncertainty then would be calculated or given by the standard deviation of our measurements. So type A uncertainties, we can use statistical methods to actually get the uncertainties of type A errors or type A uncertainties. Type B uncertainties, on the other hand, these we cannot estimate them by repeated measurements. These are based on intelligent guesses or scientific judgment of non-statistical uncertainties associated with the measurement. An example would be, we have an N gas, for example, or an NDW of a chamber. We have no control of that NDW. We did not establish it. Or what we can do, we can repeat, the radiations, get multiple R's. We can estimate the uncertainty in the readings, for example, but we cannot estimate what is the uncertainty on the NDW. So what we do, we look at literature, for example, or maybe standards lab. We look at some paper, or maybe just do an intelligent guess, and then try to use that uncertainty to estimate the overall uncertainty in our measurement. So NDW, when it was established, remember, there are a lot of factors. There are stopping powers. There are correction factors. A lot of factors are involved in the NDW. There are researchers who are doing this through Monte Carlo or by other means in order to give us an estimate of the uncertainty in that quantity. So this will be type B errors, include influences of the measuring process. Uncertainty, for example, when we're measuring the dose, yes, we repeated the experiment R several times, but how about the depth, for example? How accurate is your depth? There is an uncertainty, or accuracy of your position. It could be actually due to correction factors. We have tables for stopping power ratios, for P replacement, and so on. But these, they have uncertainties in them. Densities, for example, of a material. That's an example of physical data. Or, for example, the WE over WR over E. Yeah, 33.97. But there is an uncertainty in that one. So type B standard uncertainties can be derived by estimating a limit. Maybe we cannot measure it or do some statistical analysis on it, but we can have sort of a good judgment. We can say, okay, we've measured the dose, but probably it cannot be, for example, more than 2% or more than that. It has to be within a certain limit. So it's based on our judgment. We're setting a limit on that, and then based on that limit, we can then give it, an uncertainty for type B. تمام. So the next property we like actually in the dosimeter is the linearity. Linearity, what we mean by it is basically we want the dose, we want the reading of the dosimeter to be linearly proportional to the dose. We expose that we have a device reading, let's say a chamber reading is 1 nanocoulomb for, let's say, an exposure of or a dose of 2 centigrades. Now, if we double the dose, we want this dosimeter of our chamber to read 2 nanocoulombs. Okay, so it has to be a linear proportion. This is something we desire. Okay. In other words, so if the amount of radiation is doubled, we want the signal from our dosimeter to also double. So that makes a linear dosimeter. The advantage when having a linear dosimeter is that when we want to calibrate this dosimeter, we can do it through one single measure. We put the dose, or put the dosimeter in a location where the dose is known, and then we irradiate, we take the signal. So the dose divided by the signal, that is actually the calibration factor of the dosimeter. However, if the dosimeter is not linear, then I don't know this guy, Michael. So a linear dosimeter, this would be the response of a linear dosimeter. Slide. Okay. So if we double the dose or the dosimeter reading, the signal we're getting is linear proportional to the dose. Sometimes some dosimeters might exhibit a linearity in a certain region, but in other regions, they do not exhibit a linearity. So in that case, we have to be careful where we're going to use the dosimeter, which region. If we are in a linear region where the dosimeter is linear, then okay, we can, if we want to get a calibration factor for this dosimeter, we only need 1 point in this slide. We need a signal and we need to know the dose. However, if the dosimeter is nonlinear, in order to establish this curve, because this curve defines or describes the behavior of the dosimeter with dose, then we probably need to do multiple readings or do a calibration to establish this curve. So we need to, for example, get the dose, put a given, let's say, value, get the reading, and then maybe double the dose. The same thing, we get the reading, and so on. So chambers are known to be linear dosimeters, especially in the range in radiotherapy. But films, on the other hand, films are non-linear dosimeters. So if you want to do good film dosimetry, we need to establish a full calibration curve of the curve. A chamber is probably, we can take one reading, we can put the chamber in a location where the dose is known, get the signal of the chamber, divide the dose by the signal, that defines our calibration factor, and we can use it to determine the dose as long as we are still in that region where the chamber behaves linearly with dose. This is here an example of also a non-linear dosimeter. In this part, it's linear, but then if we want to use the dosimeter in a different region where it's non-linear, then probably we need to establish this curve by doing multiple measurements, not to a single point. So this is an example If we want to test if a dosimeter is linear or not, what we do, we put it in a radiation beam, and we start to deliver it to give it known doses. We double the dose, and we look at the signal. And then we plot the signal versus the dose, and we see if that is a straight line or not. If it's a straight line, then it's a linear dosimeter. If not, it's non-linear. Dose rate dependence. We have some integrating systems. Sometimes you want to measure an integrated response. For example, a chamber, we want to measure a charge, not the current in the chamber, because actually the chamber or the electrometer will register the current. But we want to measure the charge, for example. So it's important that the dosimeter does not change its response to dose with dose rate. Another, or just an example for this, we are going to give the chamber 100 centigrades. We want the reading of the chamber to be constant or the same, irrespective of how fast we are going to deliver that dose. It doesn't matter if we're delivering 100 centigrade in 1 minute or in 1 second. So that's what we mean by dose rate dependence. We want the dosimeter to be independent of the dose rate. So ideally, the response of dosimeter system, this is the signal divided by the dose, at two different rates. Those rates should remain constant, independent of the dose rate. In reality, this might not be true, and the dose rate might have influence on the dosimeter readings, and thus appropriate corrections are needed. Ionization chambers, luckily for us, in our dose rates used in radiotherapy, typical external beam radiotherapy, does not really show a dose rate dependence. But if we start to use the chamber to go to regions where the dose per pulse is very high, flash radiotherapy or IRT beams, then the chambers might exhibit a dose rate dependence there because of the recombination. That is the issue. What happens in the chamber is the recombination. And that's why one has to think of an appropriate dosimeter such that this dose rate dependence is minimal, or find a way to correct for the dose rates. Flash radiotherapy, one of the big problems with it is using ionization chambers. If you want to measure a PDD, that is a problem with flash radiotherapy. So directional independence, obviously we want the dose or the variation of the response of the chamber to be independent of the angle or the direction of the radiation beam. However, this is very difficult usually to achieve because of the construction, the design of the chamber and its size. So usually dosimeters will exhibit a certain directional dependence. Even for a cylindrical chamber, you might think it does not exhibit a directional dependence. Actually, it does. Just look at, I mean, this has been tested. So here, if we have a chamber, a cylindrical chamber, and we have the central electrode. This central electrode would actually not be in the center of the chamber, could be a little bit away from the center of the chamber. So the response of the chamber, the radiation beam is coming from here or from here, it might actually differ. Some estimates that this directional dependence is about 0.3% in cylindrical chambers. And if you notice, if you look at the chambers we use, they will have probably a dot on the chamber. And the reason of having the dot is just to guide the user. Maybe if you want to reduce this directional dependence, is probably you keep that dot always facing the radiation beam. This is of importance if we are calibrating the LINAC. If we're calibrating a LINAC, probably we want to reduce the uncertainties as much as possible. So when we send the chamber to a standards laboratory, they are going to calibrate the chamber position such that the dot is actually towards the beam. And when we are when we use that chamber to calibrate our beams, it's also if we want to eliminate or reduce, let's say, this directional dependence, it's advisable that we put the dot of the chamber, that dot towards the direction of the beam. But sometimes this is not avoidable. We have some nice chambers used for we have some chambers used for, let's say, electron dosimetry or whatever. They have some desirable quantities, properties like spatial resolution. But the problem with paraplate chambers is that they are affected by direction of the beam. So the positioning of the chamber, when you position it in the phantom, we really have to be careful. This is a plot showing that how the response of the chamber, of the reading, is affected by the position or the angle, direction of the beam with respect to the chamber. And it's not something not negligible. It could be about a 5% or even 10% lower based on that. Energy dependence, this is also an important or desirable property for a dosimeter. Basically, or an ideal dosimeter would have no energy dependence. We want this dosimeter to have a calibration factor established, let's say, on a given beam energy, and we want to use that exactly the same calibration factor for all other energies. So that would be the ideal dosimeter. So the advantage would be that the dosimeter can be calibrated in one energy, for example, cobalt, and then we can use that dosimeter to get the dose in a different energy. Okay? These are two famous examples. Films. This is a galvanic film, an EBT galvanic film, and this is a calibration curve. The dose versus optical density, I think, measured optical density. And these curves were obtained with multiple energies, over 60, 150 kV, and so on. And based on the data, these curves are energy independent. So it doesn't matter which energy we use to deliver the dose, as long as the dose, then this is the response of the chamber. On the other hand, here on the left, we have a radiographic film where it shows strong energy dependence. This is a calibration curve. We use the film and we deliver what we've done. We delivered the dose using multiple different beams. And these response curves are different. They are not the same. So if someone, for example, obtained this calibration curve on this beam, we cannot use the film to measure a dose on this energy, 28 keV. We need to establish an energy response curve in that energy before we could use the dosimeter to measure doses in that energy. So this is an energy dependent dosimeter, and this is an energy independent dosimeter. Spatial resolution. So this is Obviously, we would like to always think of an absorbed dose to be a point quantity. If we have a larger volume of the chamber or a dosimeter, that means we can have some issues with, especially if we want to have high spatial resolution, then we could have a volume averaging effect that could actually give us incorrect results. Finally, convenience of use. For example, some dosimeters, they could be reusable and some are not, single use. Ionization chamber is a reusable dosimeter, whereas a film is a single-use dosimeter. So sometimes we would like to actually use a reusable dosimeter. Sometimes we want to actually use a single-use dosimeter. So I cannot say which one is better. It depends on the user, what they want. Some dosimeters are sensitive to handling, while others are not. TLDs, for example, one really needs to handle them carefully. Needs to wear some gloves and handle them with tweezers and so on. Some might not really that sensitive to how they're being handled. Some dosimeters can give the reading instantaneously. You put the dosimeter, you get the signal immediately, while others require time to obtain the signal. TLDs or film dosimeters, we need to leave them for some time in order we start to read the signal and get the dose from them. Yeah, so there is one I did not talk about. It's basically the environment. They're not affected by the environment. Let's look at the list. I think I missed one of this. So we want them not to be affected by an environment. Ionization chambers, when they're open to temperature and pressure, the response of the chamber will depend on the air density. So the temperature changes and we're delivering the same dose, the signal is different. So that means we need to find a way to correct for this. Any questions on the first part about dosimeters and properties? Because now I'm going to go through some of typical examples of dosimeters. Okay.
Sir, I have a question.
Yes.
So regarding the dose rate dependence, is there any way to determine this for any detector, or is it something that comes with the specs or by the laboratory that do the calibration?
Probably there are ways to account for that. How it is done, really, I don't know. Probably the manufacturer or in the literature, they will show you ways to actually change or correct for the dose rate dependence. The only example that I have faced, honestly, was actually ionization chambers when they were used for an interoperative beam. So the way we had a problem even to how to measure a PDD using a typical chamber. We had a Roos chamber. A Roos chamber has an it's about 2 millimeters. Okay. So the issue, 2 millimeters. So the issue was a recombination. When in an electron beam, this is how the PDD, we expect it to look something like this. So here the signal is very high. Whereas here, the signal is lower. So the recombination correction factor here is going to be different than here. Because here, well, we're going to lose, there is a higher chance of losing actually the signal due to recombination because of the high density of ions compared to when we are in this region. So if we just take the pure signal without any corrections, definitely the PDDs that we're going to get are going to be wrong. They're not going to be the true doses, the true PDD. Because we are having an under response here of the chamber compared to heat. And this happens when we're dealing with high dose per pulse beams. In our typical Linux, that's not really a big deal. Even if you go to 1,000 MUs per minute, let's say those rates, it's not really a big deal because what we're talking about is the dose per pulse. The dose per pulse, that what affects it's that ionization density in the chamber. So how do we deal with this? Should we apply a correction factor? You know, because there are ways to actually obtain what is the ion combination factor for such scenarios. It's not based on the 2-voltage technique, but it's more like it's a more complex way of doing it. Should we then, at every depth, we apply we measure the recombination factor and then apply, correct the signal for recombination? What should we do? So the best way, the best suggestion is actually use a smaller dosimeter. So use a dosimeter that has 1 millimeters. So recombination is still going to happen there, but at least we are reducing it a lot because the volume is now smaller. So the ions are collected faster. We're not giving them space to interact with more ions for recombination. So we shifted. We had to use a 1 millimeter Marcus chamber. We could use, for example, a pinpoint cylindrical chamber. We're reducing the volume just so that we reduce as much as possible this recombination, because then we don't want to deal with the corrections of the dosimeter. Okay, so that is my experience with dose rate dependence. Diamond detectors, these are new detectors coming in the market, and they do actually exhibit a dose rate dependence. So even in a clinical beam, when we want to measure a PDD, the PDDs measured with diamond detectors compared to, let's say, a farmer detector or a typical ionization chamber, they're different, but the beam is the same. And this is due to the dose rate. It's due to the dose rate. So probably researchers or the manufacturer will tell you how to handle with these. You just have to be careful when you get a dosimeter, and suppose it's a new dosimeter, then probably you want to do some testing on dose rate dependence, especially in the dose rates that you're going to use dosimeters at. Okay.
Okay, thank you so much.
Okay. So the first dosimeter, so now I'm going to move to some examples of dosimeters or calorimeters. Calorimeters, basically, these are huge, or nowadays they're smaller in size. But the basic idea is we try to measure change in temperature in order to get the dose. So the signal, the reading is changing temperature. And then the quantity that we want to ultimately get is, absorbed dose in mean. There are two types of calorimeters that are used currently in standard lab. One is a graphite calorimeter. This is a graphite calorimeter, where basically when we put this, what we do is we measure the temperature before we shoot the beam, and then deliver some radiation there, and then we measure the temperature of the dosimeter after it has been irradiated. So the change is due to radiation, and then we can somehow relate that to the absorbed dose in the dosimeter. This is here a water calorimeter. It's even larger in size, and so on. The problem with these dosimeters, the change in temperature is very small. It's of an order of a 10 to the power minus 5 kelvins. Very, very small per grade. So if you deliver 1 grade, the change is very small. That's why these dosimeters need to actually be insulated from the surrounding, from the room. Otherwise, a small change in room temperature could actually produce a signal larger than the signal of the dose. And that's why, or sometimes they in vacuum, like for a graphite calorimeter. So although the concept of using them is really very simple, but in practice to apply it is really difficult, very difficult. So if you have a sealed water calorimeter, this is use of a low thermal diffusion of water, which enables the temperature rise to be measured directly at a point in continuous water. So we have inside here at a point in this water phantom, we have maybe a thermocouple, something that's going to measure the rise of temperature in that. Of course, if the water itself is actually moving, that could generate heat, even larger than what's being produced by the radiation beam. So that's why these devices are very bulky. Usually, you cannot use them in the clinic. They're used at standard laboratory. So this is an example of how it works. So basically, this is a water calorimeter. So basically, the basic idea is that we measure the temperature, okay, or the change in temperature. That's what we want, the change in temperature due to radiation. And as I mentioned, the change in temperature is usually very small. It's about 10 to the power minus 4 or minus 5 per grade. It's very sensitive to the environment. And that's why it must be thermally sealed. You don't want any exchange of heat between the water, for example, and the room. Very bulky. That's what makes them very bulky. And they're limited to use in primary dosimetry standards laboratory. So the dose equation looks, very simple. We have C is the specific heat for water. Okay. And the nice thing about this quantity is you can establish it without a radiation. So this has been known for a while, some thermodynamic experiments, physics experiments, without ionizing radiation. They have determined this specific heat capacity of water. Basically, it describes the change in energy, heat, okay, per unit Kelvin, per unit kilogram. That's the specific heat of water. So if we can measure the temperature, delta T, before irradiation and after radiation, well, that will tell us how much energy was deposited in the water per gram. And that is the dose. Okay? The problem with these devices is, okay, maybe the heat that with the radiation beam is not all used actually in heating the water. Some of it actually some of the energy deposited by radiation might do some chemical changes because ionizing radiation is going to ionize and so on. So there is always a correction factor, and this is what we call a thermal defect. If all of the energy by radiation deposited in the fat, in water, imagine all of it was converted into heat, then this thermal defect is zero. None of that energy has been actually used in other places, like in breaking chemical bonds or something like that. But in reality, there has to be some heat defect. And determining this heat defect, this also it has some uncertainties. But the nice thing about any calorimetric system is that this specific heat, especially for water, this is established independent of ionizing radiation. And this is why these calorimeters are always put into this category of absolute dosimeters. They will give us the dose absolute. Okay. So how do they measure this change in temperature? They use what's called the Luminescent bridge circuit. So basically, we have a simple circuit like this. This is a simple circuit. And here Rx is a variable resistance. We can change the resistance of this, we change the value of this resistance. And this resistance, this is what we're going to put actually in water, in the place where we want to measure the flow. So before irradiation, and we have here something that reads the potential between these 2 points. So with this variable resistance, we can change it until the voltage read by these 2 points is 0. There is no voltage, so no current goes through this line. Once this happens, then we say that the bridge is balanced. When there is no reading, no voltage, the bridge is balanced. And when this bridge is balanced, the ratio of this resistance to this resistance equals to the ratio of this resistance to this resistance. So once, imagine we design this, we put it in water, and then we tweak, we play with this variable resistance, and then, okay, at that value, we know we can determine what is the resistance of A. We have it there. These are known. Now, once radiation, we shoot the beam, the resistance, and this resistance of A is inside the beam at our point of measurement. The resistance of this will actually change with temperature. So if at that point the temperature changed, the resistance is going to change. So when the resistance change, okay, the bridge is not balanced. We are going to see a voltage here. So what we need to do, we need to change, this resistance such that now we're getting back no voltage here. So it's balanced. And this will allow us to determine what was the change in the resistance. So we have the resistance before the radiation, and now we're going to measure the resistance after the radiation. So now we have these 2 unknowns. We can then determine if we know the temperature or the change in temperature, that's really what we want. Then we can actually get a differential equation from here. And we can then determine by how much the temperature actually changed. So that's the basic idea of how this Luminescent bridge works, or how we're measuring the delta T temperature. Okay. So this is a summary of calorimetry dosimeters. What is the signal for this dosimeter? It is actually the change in temperature. I often ask, some of the students, so what is we have a chamber, or we have whatever dosimeter, okay, what's the signal that we're measuring, or what does it measure? Okay, they always say it's a dose, it's exposure, and so on. No, actually, dosimeter does not give us that quantity directly. It measures something. It gives us, we use a signal, and the signal for calorimetry, these are the change in temperature. One of the problems they have is that they are not precise. Remember, if we repeat the measurement several times, the readings are not going to be the same. Okay, so we're looking how close are the readings. That defines the precision. So it's very challenging. That's why it's a very small change in temperature. Think about it. A small change for these doses, very difficult to measure these changes. That's why they usually give us, different readings, okay, or they have a high standard deviation, but they're accurate. and they're actually considered to be the most accurate. So if we repeat the experiment about 10, 20 times, then we're going to take that average value, and accuracy comes from the specific heat. We know the specific heat very well. Although I think some people's claim, yeah, we do know that, but there is this heat defect or thermal defect. We don't know it well. However, it's considered to be actually the most accurate dosage. Dose dependence, yes, it's linear. Dose rate dependence, it has no dose rate dependence. So it's a linear dosimeter. That is something nice. So in effect, if the change in temperature doubled, then we know the dose has doubled. That's what we mean by a linear dosimeter. Dose rate dependent, I don't think there is any dose rate dependent. I might be wrong. Energy dependence, no, because measures just change in temperature. The specific heat, that's a constant, has nothing to do with the energy of the beam. And then, so it's energy independent, does not exhibit any energy dependence. Directional dependence, I don't think there is directional dependence, because it's this resistance or the thermocouple. That's what's measuring the dose. Convenience of use, I think all of you will agree that we don't want to see such a thing in our clinics. We don't want to use it. Okay, very bulky. And it's only limited to be used in dosimetry standards laboratories. Although I think there are some efforts to actually the graphite calorimeters. Maybe one day we're going to see them used in the clinic. Because if we have them in the clinics, then we don't need to calibrate, we don't need to send them to be calibrated. Okay? We don't need that. So anyway, we're going to move to another example of a dosimeter, a chemical dosimeter, so a freaky dosimeter. So basically, this dosimeter depends on oxidization of ferrous ions. So we have iron 2+. When it's irradiated, some of that ion in a solution will be converted to Fe3. Okay. So the idea is we have a solution. Let's get a freaky solution. And for example, this here, and let's find a way to measure what is the concentration of Fe2 and the Fe3 in that solution. Once we irradiate the dosimeter, some of these Fe2s are going to be converted to Fe3s. So all what we need to know is the change in this concentration. So the basic principle is we will measure the change in concentration in the solution of Fe2 and Fe3. So we can measure these changes directly through titration, تقطير بالعربي, or indirectly through, for example, changes in paramagnetic properties that may be measured during using a nuclear magnetic resonance, or maybe using some optical techniques. So we can, I think today we have these optical CTs as 3D dosimeters. So what we can do is we have, for example, a light beam or a laser, let it go through the solution when there is no dose, and then once this dosimeter is irradiated, its opacity will change, it becomes darker. So the transmission is going to change of the same, let's say, light source or light intensity. And from that change, we can then figure out by how much the concentration of the freaky dosimeter has changed. So this concentration of ferric ions increases proportionally with dose and is measured with absorption of ultraviolet light in a spectral photometer. This is if we're using these optical or optical density techniques. Freaky dosimetry, yes. So now we have measured, change in concentration. We have measured, the change in optical density. So what? How do we still? We're not interested in the change. We're still interested in the dose. So the freaky dosimetry depends on an accurate knowledge of the radiation chemical yield of ferric ions. There is a constant, something similar to the W air over E for air, because that tells us the amount of ions or mean energy to produce an ion pair in air, or actually the charge in coulombs per joules. We have something very similar. It's called we need the radiation chemical yield. So this radiation chemical yield is called G. And basically, it's measured in moles. Moles, remember, is a concentration produced per 1 joules of energy absorbed in the solution. So this is the basic equation of dosimetry with freaky dosimeters. We need to know what's the change in molar concentration. Okay, so remember, this is moles per volume. Okay, because I was trying to figure out, does it make sense or not? And actually, it does make sense. We have the density, and we have this G value. So G value is the chemical yield. It's given in moles per joules. So this is a constant for us. So all what we need to know is the change in this concentration. And obviously, we want the density of the freaky solution. We need that. So this chemical yield is related to an older actually parameter. They were using an older parameter. It's called the G value. G value is, I like, its concept. It's basically how much ions or molecules of Fe3 we're producing, we need, or can we produce per 100 electron volts. It's something similar to the W over E or W air. W air is basically the ions produced sorry, it's the amount of energy required to produce one ion. This is reversed, it's the opposite. There, what's the energy required to produce an ion pair? So that's the value of 33.97 electron volts per ion pair. To produce one ion pair, we need 33 electron volts. The G value definition is a bit opposite. It said, okay, if you have 100 electron volts of energy, how many molecules of Fe3 are we going to get? Okay. So and that's why it is actually in the equation, it's actually in the denominator. Okay? Because per energy, per MeV, so we need that positive. So these are some of the values, recommended G values in molecules per 100 electrons. For photon beams, ICRU 14, they list them, and then for electron beams, ICRU 35. So the value, this is what it means. It means that if 100 electron volts, we have an energy of 100 electron volts, this could actually produce 15.5 molecules, transform 15.5 molecules to Fe3. That's what it means. So the G value, one of the things, it is not really energy independent. So obviously this makes the dosimeter energy dependent. It's not like the W over A, W air over E, that was constant. So at least to get the dose in air, it was a radiation independent or energy independent dosimeter, energy chambers. The problem we face is we're not interested in those in air, we're interested in those in tissue or in media. So these conversion factors related to, these are actually energy dependent. That's our problem there. So some are of chemical dosimeters. So the signal probably is change of chemical concentration. We have concentration of one type of molecule. Now this concentration is going to change because of radiation. We could also think of it as, the change in light transmission, optical opacity. If we are not going to measure these concentrations, something else has changed, which is the opacity of the solution. So we can measure the change in this opacity, and that will be our signal. Or it could be the change in some paramagnetic properties. So maybe some relaxation times changes. I have no experience with freaky dosimetry with MRI, but something changes because of those, then that is a signal. So whichever path you want to use, okay, that would be the signal, the dosimetric signal. Precision, yes, although they're less than ionization chambers, better than calorimetry. Accuracy, they're acceptable, but less than calorimetry. The reason is this G value. This G value, remember, the conversion factor for calorimetry, which is the specific heat, that was established without the use of ionizing radiation. However, this G value, you cannot establish it without a radiation beam. So this is why sometimes they put this at a second, let's say, level compared to calorimetry in terms of accuracy. And sometimes they're called the reference dosimeters. Air, for example, chambers, they're also called reference dosimeters. The reason is this quantity W air over E. You cannot establish that constant, which is 33.97, without radiation beam. You don't have an alternative. In Freaky, it was the G value. Still, that G value could not be established without radiation beam. However, the specific heat for water, yes, you could establish it without radiation beam. So that's why calorimetry was termed as absolute. However, Freaky and ionization chambers, they were, called reference dosimeters. So often, if you look at some of the protocols, they'll say reference dosimetry. They will not say absolute dosimetry with ionization chambers. So reference, although it gives us a dose at the end, but somehow, they like to term it as a reference because this calibration factor or conversion factor, it cannot be established without the use of radiation beam. Dose dependence, so it's not really a linear dosimeter. It could be a semi-linear. That means probably if we want to use it as a dosimeter, we have to establish a calibration curve, a full calibration curve, in order to use it as a dosimeter. Dose rate dependence, I believe it does not depend on the dose rate. I might be wrong. This energy dependence, no, because the G value, I think there is a small energy dependence. This should be yes, because when I look at the equation, this G value is energy dependent, but maybe the dependence is small. So if you establish it in cobalt, then probably it's good if you establish it in another. You can use it in another beam without really applying some protection factors. So maybe that's why its term does not have energy dependence. Convenience of use could be used as a 3D dosimeter, but required an MRI or an optical scanner for 3D dosimeter. So the reader of it is really very expensive and so on.
They also need to be read out immediately after irradiation because they diffuse with time.
True. Okay, so this is okay. So you see, there are some issues with them. Some dosimeters, we actually want to leave them, like TLDs and films, but maybe you're right. Here, probably we need to, they need to be read quickly, especially if we want to do like dose distribution. Sometimes we're not interested in that, but anyway, probably you know more than me in this topic. Okay. Ionization chambers, we went through this in details, I think. Okay. So it's basically a gas-filled cavity surrounded by a conductive outer wall and having a central collecting electrode. This is after talking about the cylindrical ionization chamber. There are other devices. I did not have time to prepare the slides, but I wanted to talk about another type of ionization chambers, which is the free air ionization chamber. This is also used primarily in standards laboratories, and they're used to measure exposures. That's what they're used for. Their design and is a little bit different than what typically we use in the clinics. In the clinics, we're interested in measuring the dose, whereas a free air ionization chamber is used actually to measure exposures. Maybe next lecture, maybe I can talk about it more. So chamber and electrometer, of course, you all know this is such an image. Okay, so this is the dosimetry system. And here we have a temperature and pressure. So chambers, they do actually, because they're open, these type of chambers. So, okay, they're affected by the environment. So different designs, for example, we have typically a cylindrical chamber. This is probably the most popular design for chambers, independent of radial beam direction. Typical volume between this is typically the volumes. We can have very small for the micro cylindrical micro or semi. So we can have, for example, at 0.6 cc. This is thimble, and then we have a mini. I think dosimeters in ionization chambers. They have a volume of 0.1, and then we have one that have very small volumes of about 0.01 to 0.05. Typical radius could be between 2 to 7 millimeters, length 4 millimeters up to 2.5 centimeters. They usually have a thin wall, and they're used for electron, photon, and ion measurements. We have paraplate chambers. Okay. These are recommended for dosimetry with electron beams with energies below 10 MeV. Very useful if you want to measure those measurements or even to calibrate the beams. They possess a good spatial resolution in the depth direction, but if you want to measure profiles, of course, they're not good. They're good also because of their spatial resolution for measuring surface doses, whether it's in photon beams or in electron beams. This is talking about in the build-up region. A third type of ionization chambers in the clinic, these are the well-type chambers. They do have high sensitivity, useful for low dose rate sources, like those used in brachytherapy. They do have actually a large volume. Can be designed to accommodate various source sizes. Usually calibrated in terms of the reference air curve, or they can give us an activity of the source. Okay, so typically, this is the chamber. This is the wall. Okay. So the source drops somewhere, and then we have this is the outer electrode. Imagine this like 300 volts, and this is the electrode. So we're measuring in this air region. And finally, we have a monitoring chamber. Every LINAC probably has a monitoring chamber. And their main aim is actually for stopping the radiation or monitoring the beam symmetry and flatness. And these chambers, they're usually sealed. Some LINACs, they have open chambers, but then if they're open chambers, then since these chambers, they are affected by the environment, by temperature and pressure, then you really need to correct the signal, because the signal is going to change, and that change is not because of the dose. It is actually due to density of air inside the chamber. Also, this is the fifth is another design. We have a segmented chamber, array of chambers. This is an old problem. I don't know if they're using them nowadays or not. But such a device was used to actually get planar doses Often they were used for IMRT QAs and so on, or even just for QA for Linearity. So we have multiple chambers within a 2D array of chambers. But I think they're phasing out from the market. We're getting the silicon diodes. I think those are because they have better or higher spatial resolution than Ionization chambers. So summary of Ionization chambers: precise, yes. Often we repeat the experiment, we get the same dose. One of the problems we might face is if the chamber volume is small. Remember, we talked about this Compton current happens that radiation beam will induce a non-dosimetric signal. So if the volume of the chamber is large, then often that dosimetric signal, non-dosimetric signal is very, very small. But the problem comes when the dosimetric signal is low, comparable to this Compton current. Then we need to do some corrections there, whether we do polarity effect corrections or whatever. So the accuracy, they have reasonably, they have acceptable accuracy, but of course they're less than calorimetry. First of all, we have or any calibration factor for a chamber needs to be established in a standards lab. So there are some experiment errors when establishing the factor for the chamber and so on. Dose rate dependence, yes, they will exhibit the dose rate dependence, but not really. I don't believe we see this in our typical linear-based clinical beams, but this could be actually in high dose per pulse beams. Energy dependence, yes, they do have energy dependence, especially when we're talking about we want the dose to medium. So they will, that's why we have these correction factors. These correction factors will depend on the energy. Directional dependence, this is design related. Although I think still a cylindrical chamber might exhibit a very small directional dependence, but might be negligible if you're measuring, let's say, a PDD or measuring something that's really not important, not related to the direction. Convenience of use, they do not require special handling. But open chambers, they're affected by the environment. So if you want to know the dose accurately, we need to take care of, temperature and pressure. And there are some other factors like polarity effects, ion recombination. So you have to judge, are these factors important, what I want to measure, or maybe I could neglect them. So maybe in the case of absolute dosimetry, we probably need to take account of them. But if we're doing relative dosimetry, measuring a PDD or TMR, maybe these factors are really not important. Even temperature and pressure, as long as you're doing the measurement, at roughly the same time, with no change in temperature and pressure. Luminescence dosimeters. So luminescence dosimeters, these are crystal structures which are able to trap or store energy when irradiated. So we have a crystal, it could have some impurities there. When it is irradiated, usually, electrons are going to be excited to higher levels. These are called conduction band. And many of these electrons are going to then drop back to the valence band. And when they do this, they will emit light. But luckily that some of these electrons, they will actually don't go back to the valence band. They will remain in that conduction, or they will actually be in a hole, in an energy trap. So what we need to do is, so they're storing some information. So to read, this dosimeter is, we try to look at how many of these electrons are trapped. And that number is going to be proportional to the dose. The more dose we're giving that dosimeter receive, the more electrons are going to be trapped. So the challenge or the way is this. we try to somehow excite these electrons, give them a small energy, and this will help them back to come to the valence band. So when they do this, they will emit light. So if we have the dosimeter radiated, many of the electrons that were excited to the conduction band, they will actually drop back to the valence band. So while the beam is on, yes, we have emission of light from this dosimeter, but some of these electrons will be trapped. So after we finish irradiation the dosimeter, then if we can excite these electrons, trapped electrons, and encourage them to drop down to the valence band, then when they do this, they're going to emit light. So if we measure the light, amount of light, that will give us, that will constitute our dosimetric signal. These are, the nice thing about them is that they can come for different shapes and sizes. They could be, some of them actually could be excited using a light. So these are called OSDLs. The ones that are excited by heat, these are TLDs, thermoluminescent dosimeters. So when used for purpose of dosimetry, the material is called the thermoluminescent material and the thermoluminescent dosimeter TLD. Okay. If the exciting agent is light, then the phenomena is referred to as optically stimulated luminescence, OSL. So OSLD, this is an optically stimulated luminescence dosimeter. And I think they're becoming popular in the clinic. So this is a dosimeter. This is a reader of the dosimeter. And I think this is for an OSLD. Properties of these dosimeters. Maybe the energy can then be okay. So in terms of precision, yes, we could have a good reproducibility, especially if they're handled carefully. We could get them up to 2% reproducible, but you need to handle them very carefully. Accuracy, acceptable accuracy, but obviously these are less than calorimetry and probably less than ionizing chambers. Those dependence, they don't exhibit any dose dependence, so we can think of them as linear, although I think if at very high doses, probably they will lose their linearity, but at least in the range of radiotherapy doses, these are probably, one can consider them as linear dosimeters. Dose rate dependence, I'm not sure. I don't know why I put Y yes there. Maybe this is a typo. I'm not aware if they are dose rate dependent or not. I have to revisit this. I really don't remember. Energy dependence, yes, they exhibit a little bit of energy dependence. So a TLD, if they're calibrated in, let's say, 6 MV photon beam, okay, if you want to have good dosimetry, good lower uncertainties in the dose, use them for that particular energy. If you want to move to another energy, do a measure to another energy, you need to calibrate them in the other energy and so on. Directional dependence, this will be dependent on the design. Convenience of use, reading is taken after 6 hours or more. And they need careful handling. You know why we need to take reading after a few hours, 6 hours or 12 or a day? Do you have an idea or? Because usually, and I know this for TLDs especially, some of the energy, so remember the signal is, okay, the number of trapped electrons. Now, some of these trapped electrons might actually gain some energy, even at room temperature, and they will emit, the signal. They will emit light before reading them. So these are called, I forgot their name, glow peak. So it's a glow curve. Yeah. If you look at a typical, so if you have a TLD, and if you plot here temperature, and here we're plotting the intensity of light. So you will have probably a peak like this. So this is at around 300 degrees Celsius. Okay. And this here would be something around, let's say 30, 40, 50, let's say, degrees. Okay. So this is basically after we radiate the TLD, we start to see the intensity of light. We measure the intensity of light as a function of temperature. So when the TLD is at room temperature, there is going to be some emission of light from them. And this is why this is going to be a big source for uncertainties in our measurements. Because we don't know if we left it, let's say after 1 hour, half of this peak was actually emitted or all of it, we don't know. So the best way is we wait for 6 hours or more. And by waiting, all what we're doing, we're actually letting the TLD get rid of this peak, emitting the light, okay? No more these electrons, this energy, they're over there. So when we read the TLD after waiting for a certain hours, then the signal will be the light emitted with this temperature. And this should stay stable because they only glow at higher temperatures. Room temperature can affect this peak here. So a proper way to do dosimetry with TLDs is you need to have some discipline. You need to, for example, or when you calibrate the TLDs, calibrate them, for example, let's say you shoot them, let's say at 3 o'clock or end of the day, and then you wait the next day, let's say 12 hours, and then you read the TLD. So we know, for example, the dose that we delivered to the TLD, and now the reading is based on this light intensity. We know then, okay, we can get a calibration factor for the TLD. When we want to do a measurement with the TLD, let's say on a patient or any other purpose, we need to have the same discipline. We record when was the radiation done, and then we read the TLD after the same amount of time has passed. That is the proper way of doing dosimetry with TLDs. So obviously, we cannot give immediately the dose to, let's say, a physician requiring what's the dose based on TLDs. We need to wait for some time. So that's a disadvantage, but they're good if you, for example, want to monitor the dose received, for radiation protection. This is a good dosimeter because then it keeps the dose. We read it after 3 months, and that's it. Film dosimeters. So with the film dosimeter, what we do, we place a film, and we have a light source. Think of a light source. We shoot a beam, and then we look at we measure the intensity of light. So what we do with film dosimetry is before we radiate the film, we actually put the film, shoot the intensity of light, and then measure shoot with the light source. We measure the intensity. Now, after the beam, after the film is irradiated, then the opacity of the film is going to change. This means that more and more of light are going to be attenuated in the film, and the intensity is going to drop. Okay? Since this intensity is a signal of this opacity, and the opacity is somehow related to the dose deposited by the film, this now becomes a dosimeter. So film dosimeter, there are two types. There is a radiographic dosimeter. It's based on silver bromide crystals, and basically with irradiation, we convert these ions of silver into black silver, actually. Anyway, this is like this is an old, I think, old technology or basic principle of how films are actually used. So what happens is when the films are exposed, we need to process them using the chemicals in a solution. And what happens is that this chemical is going to then wash away the silver that did not actually become metallic silver or black silver. So we have silver ions. When they're radiated, they become like this black silver. And what remains is actually the black silver in the film. A radiochromic film works a little bit different. So they have consists of a special dye that is polymerized and develops a blue color upon exposure to radiation. I don't know if these are blue color. This is the old chromic films. Newer ones, I don't see a bluish color. But anyway, it's a bit different technology, or the way they work is a bit different than radiochromic films. But the nice thing about it is that it self-develops. With radiation, the opacity of the film will start to develop on its own. We don't need a solution. We're going to dip the film and remove the silver and so on. So it's self-developing. And this might also be an issue that maybe we also need to have some discipline when we're using film dosimetry. We irradiate at a given time, we wait 12 hours or 24 hours to read. Okay. The nice thing about the film dosimeters is that the signal remains there, not like TLDs. TLDs, if you read it 6 hours, the signal is gone. But with film dosimeters, we can read it at 6, at 12, at 24, the same film. The signal is not gone. But of course, the film can be used only one time, whereas the TLD, we can use it multiple times. This is an example. This is actually from the work of Ibrahim, where we calibrated the TLD, we recalibrated the films. We just put some films and we shoot them with different doses. And as you can see, as the amount of dose deposited to the film changes, we get a different opacity of the film. So the way they're read is using an optical, this optical density. We measure the intensity of light going through the film or the chain. And this change is expressed as an optical density given by this equation, the log of base 10 of the initial intensity. So this is the intensity of the film before irradiation divided by the intensity of the film after irradiation. Okay. The nice thing about the films, well, at least the chromic films, as I showed you this curve, this is actually shows that they do exhibit a dose or energy independence. So we can calibrate them at a given energy and use it for other energies. The disadvantage is that they are not linear dosimeters. So we need to go and measure or get a calibration curve for this dose. That's the for this reading or optical density. This is the dose and so on. So it's not a linear dosimeter. Here on the left, we have radiographic films. Again, they're not linear and they don't show any, or they do actually exhibit energy dependence. At least chromic, they don't have energy dependence. So in summary, they're precise, but with careful scanning protocol. These are chromic films. There are issues, for example, on the film, the direction of scanning. That was a big issue. But I think newer versions of films, they do not exhibit this directional dependence, how you're going to put the film in the scanner. Accuracy, yes, but again, with careful scanning protocol, those dependence, they're not linear. Okay. So they do exhibit, dose dependence, dose rate dependence. We haven't seen any dose rate dependence on the films. Energy dependence, they're not energy dependent. Now, chromic films, I think this is one of the big advantages. They do have a very high spatial resolution because they're often read with a laser scan or with a scanner. So the spatial resolution is really very high. Directional dependence, I don't think they exhibit any directional dependence. Convenience of use, reading is taken after 6 hours or more because we need to give it some time for development. Also, another thing is that they probably need to be stored in a dark, dark envelope and so on, because they could be affected by light. So I finished today's lecture. It was a bit long, but we have 10 minutes to spare. Any questions?
Sir, I have a question. So for the chromic films, so you prefer that we do the calibration of the films at our facility?
I don't think you calibrate the films, you send them for calibration.
I mean, we established this curve. It's not something that comes with the with the film from the manufacturer, right?
Yeah, we do. We establish the curve, yes.
Okay.
So usually we calibrate them with using our radiation beams, and we establish a calibration curve for the film. And for chromic, I think I have talks on this. With chromic films, actually, there are 3 channels because we scan them, red, green, and blue. And dosimetry is usually done with the red channel, sometimes in the green, but the blue channel does not show any, cannot be used as a dosimeter using the blue channel. So for chromic, it's not just the light intensity, but we actually need to decompose, the color of the film when they're scanned into red, green, and blue components. Also, some issues about the scanner. The scanner, you probably want a transmission scanner when using them. So in a transmission scanner, I don't know if you know about this or not, but so basically the scanner, the way it works, it has a light source, yeah, and here on that glass, you will put the object that you want to scan, yeah. So what happens is that this emits the light, and then it gets
Sir, if you are drawing something on the board, we can't see it.
okay. So basically, in this typical scanner, okay, this is how I understand them. You have a very thin light source, laser sort of thing, okay? And here on that glass plate on the scanner, this is where you're going to put your piece of paper or... So what happens is that usually if you look at any scanner, a regular scanner in your office, you will find on the lid, you will find a reflective surface. It will be like white, okay, reflective surface. So when light goes through the object, there is going to be some dispersion, and then it's reflected from this surface, and then it's going to be there's going to be also additional dispersion. So in order, if you want to really have good spatial resolution, the best thing is this white reflective surface is removed, and you have on the other side, you have a detector, a light detector there. So light goes through the object and is detected. So we don't need this. So the reason we don't want this dispersion, we want to really have very high spatial resolution. So this is here, we have something that will read the line. This is called transmission mode. So the reading is transmission mode. That's the best. You can use them to, for films, usually the reading has to be done with transmission mode. If you do it with this reflective scanners, you're just going to lose a bit of, you know, the spatial resolution. So transmission mode scanners are expensive. They're not cheap. Another thing is you probably want a scanner with a 48 color fit. So the scanner will give, you know, it will construct an image, and these images are describe the intensity in the red, green, and blue. Okay. So if we're doing our dosimetry using, so basically we have an image, we have, or maybe I can just show you our work. I'm going to stop the recording now, and then we can continue.